Hi, everyone, and welcome. So the Wi-Fi industry is stuck because nobody has so far worked out how to drive down power consumption for Wi-Fi devices, at least not until now. My guest today is Dr. Ali Fard from QuantalRF, and he says he's got the solution. Watch the interview right after this. All right, hi everyone, and welcome. My guest today on TechWatch is Dr. Ali Fard. He is the CEO of QuantalRF, and also the CTO, by the way, of QuantalRF. And QuantalRF is doing some amazing work on RF designs, specifically analog RF designs to drive down power consumption, for example, for front-end modules for Wi-Fi. So, Dr. Ali, it's great to see you. Thank you so much for coming on.
Thanks for having me.
You have I would say, a completely novel approach to the issue of driving down power consumption. Let's bring up the slides and please tell us about that.
Yes, thank you, Klaus. We have a product family that we go under the name Elementum, which is basic principles that fundamentally describes what we do. We've gone to the roots of the problem statement of throwing just process nodes and digital correction techniques to solve some of the headaches in specifically Wi-Fi, but same problems exist also in cellular, and that is power consumption, and the outcome is typically heat when you waste too much power, essentially. And then this is an area where we noticed that many has failed the past decade or so, and as the standard is developing, it's kind of difficult to catch up to it if you haven't seized the moment at the right time. So what we've done is that we looked at, like many companies today, honestly, but maybe not in the RF, and that's a new architecture. I mean, you've seen this already happening. For example, NVIDIA's aggressive design wins in the AI space and GPUs, they didn't get there by hunting or being first in 3 nanometer, right? I mean, they've designed for a different workload efficiency, ultimately in architecture. And we're doing the same thing, but sometimes people get surprised because the domain is in the RF, where naturally it's been quite a slow market when it comes to innovation. So what we're achieving is a small bump in performance, I would say, right now. We think we can do more. So we're getting about 2 to 4 times more efficiency out of the same front-end module for Wi-Fi. We don't use any digital technique. We don't believe in moving over the system burden complexity in terms of calibrations and so forth into the digital domain. That approach, I don't think, works anymore because the workloads are so high. And if you have to calibrate things all the time and then correct for it, you're introducing latency in the system. And systems become more fragile and complex. So we're solving the problem straight shot in the analog. And we're doing it also at the lowest cost. I mean, you've seen memories are blowing product costs out of proportion. It's difficult with supply management as AI is taking a lot of that bandwidth today. So the best approach is to kind of tackle the problem at its roots and go with the lowest cost option. So not hunt the deepest nodes of CMOS, just do it in something mature, that easily and readily available anywhere in the world. And that's today CMOS SOI in 300 millimeter wafers.
Right. So when you're talking about a stumbling block, what you mean is that if you do not drive down power consumption, we're stuck with high cost of devices, right? And also perhaps form factors that we don't really want. We want smaller form factors. I mean, those are some of the factors.
That's exactly right. I mean, you have to absorb the heat that the silicon is producing. You do that by having bigger packages. Packages cost quite a bit of money today. They're roughly half the cost of the chip itself or the chips itself. And then you have to cool it down ultimately, because these products are not just like in the old days where you have one FEM and one Wi-Fi radio. You have massive MIMOs, you have 3 bands operating simultaneously and so forth. So you end up paying a lot to cool down the device, like heat sinks, fans, other sophisticated techniques. So I think today we're come to the point where if you buy RF component, let's say for $1, you probably pay about 40 to 50 cents on cooling down that device. So it's an overhead on top of what you already paid for, which again doesn't really fly. So if you look at Wi-Fi 7 or Wi-Fi 8, it's the same from an RF FEM perspective. The wideband channels is what truly makes this technology useful, especially in the era where we need lots of bandwidth. Robotics is coming next and so forth. The standard has done an amazing job. 4,096 QAM signals. We have multi-band operation. We got another gigahertz of FCC license in the 6 gigahertz, at least us in the US. All of these puts a lot of demands on efficiency of the system now, because you're throwing in everything you've got at this to get the speed and bandwidth up. And if you start off from very poor efficiency systems, you'll end up having to pay lots of money to cool down the chips around this. And with every generation that comes from the Wi-Fi standard, that typically requires you to have more pristine signal. It's more difficult to transmit and receive wider bandwidths. And so indirectly, this puts an effect on the designs on the chips, especially on the front ends, that they have to be better than they were last. And if we haven't innovated enough, well, the standard is not going to help us. It's just going to make life more hard for us. And that's where I say that we've had an architectural stagnation the past 20 years. People have built basically open loop designs. You have a very simple circuit. It's an amplifier, similar way that we built, speakers back in the old days almost. It's built sort of to work under very ideal lab conditions. And it's deployed as is in the systems. And you invest a lot, but in process, in more nodes. And it hasn't really paid off as much because you haven't been able to leverage the full physics of the products that you do. So if you look physically, and let's get a little bit technical, most of these products are made in GaAs today. And if you look at their efficiency for a Wi-Fi 7 signal that is fully digitally corrected, the efficiency of the system is less than 9%. And you started in gallium arsenide, which has 6 times higher electron mobility than silicon. And yet what we've shown, demonstrated the past 12 months, is that we can beat that roughly by a factor of 3 times. Even though CMOS has started off from physics, which is 4 to 6 times on, regardless of which dimension you look at in the physics. So what does this tell me? It tells me that the GaAs community actually left performance on the table. And that's because of the architectural stagnation. It's not because of the materials or the physics behind it. And we've now pushed the SOI to nearly to what we can achieve. We still have another 20-30% to pick up. But because of the fact that the development process is quite complex, and we're not really getting any help from EDA tools, unfortunately. As the standard got more complex, EDA tools fell behind. So you're not just innovating around architectures, you're also innovating around the tools, the flow, the design flow to get this right. So I think we still have a 20-30% more to pick up. But it also tells me that the industry has stagnated on the good materials that they have. They should have reached a performance where they were basically untouchable.
Right. So allow me the naive question of asking, why doesn't everybody do this? I suppose it's because for now, at least, you are the company doing this, and there's some patents involved, I suppose, right?
Yes. Yeah, so I mean, it's hard. RF is hard, right? And it's developed very fastly the last 20 years. And I think it's a combination of not really focusing on architecture, more focusing on process nodes, shrinking, making process nodes, the material behind it better, instead of focusing on the architecture. That's the cause number one. The second is that the tools we use during the development cycle are not just good enough. So we end up, even if we have innovative ideas, we never get to execute that in reality because the tools are far off from reality. And then you get a silicon back and how many chances does an engineering team get to get it right? A few times. And I said, you know what, you don't know what you're doing. So as a result, we move things into the digital domain because it's a little bit more predictable than it is. So what we are doing is basically self-correcting architecture, an intelligent, smart architecture that corrects itself. And this is not based on a system that measures something, calibrates something, and figure things out and brings in latency and system costs. This is a real-time distortion cancellation. Okay, it happens at transistor level. For every picosecond and attosecond, this is running in full time without anybody really need to police it. It runs on top of the system. It doesn't need any digital techniques behind it. The chip is fully analog. There's no calibrations needed. And for this reason, there's no latency and no separate, correction hardware around it. So it's an intelligent system that responds to the real world variations. This is not a lab type of chip, works great in the lab, but not reality, because conditions around RF are important. Temperature, someone blocks an antenna, what happens then? Things of real world problems. And a closed loop system reacts to this and adapts instantaneously. So I like to think of it, because I'm a car enthusiast, like an anti-spin system in a modern car. Anyone should be able to drive an 800 horsepower car in a snowy weather where you are in Europe. Yes. Because you can't predict that the user doesn't sleep on the gas pedal and hits the gas pedal badly. The car self-adjusts and forces this continuously and without really the driver's input. And that's basically the idea behind this. So I love the fact that we're doing it this way, because I get challenged sometimes and people say, what about this scenario? I'm open to try this scenario because I have put an anti-spin on this thing, and it should react regardless of scenario.
Right. And the unusual thing in this case is it's an intelligent analog system in this case.
Exactly. Yeah.
So, and that is really highly unusual in this day and age. So very cool.
It is.
Yeah, tell us a little bit about the performance.
Yeah, well, we touched about the efficiency. We've launched now mobile products, and this year we're launching our third generation of mobile platforms, and that one hits about 25% in power efficiency, which is compared to less than 9%. Again, no digital correction, so it's a drop into a system, relaxes the burden of performing all the calibration and making sure that you met all the conditions, because this is self-contained. We've also launching end of this year for the AP market, and the percentages look about 32-33% efficiency for the AP market at the higher power. Yeah. I took a look at this and said, well, can I apply this architecture into gas? That hasn't been our goal initially. And we're looking deeply at this, and we see that with our architecture, we could actually hit 45% efficiency in gas.
Wow.
That has to be directly compared with less than 9% when the system is digitally corrected. Again, even in gas, we won't have digital correction, because you can do, believe it or not, an intelligent architecture also in gas. So chips are small. The package size is really small, and with that delta in power efficiency, you can actually reduce packages, and you're saving a decent amount of time and effort and headache when it comes to the thermal.
Very good. Very good. Yeah. So far, I was just going to say the only other option really that's being pursued by the industry is digital predistortion, right? I mean, that is really what you're, so to speak, up against. So it's either this or digital predistortion. Those are the options, right?
That's it. Yeah. And when you go digital predistortion path, you bought the car and it only came in black with those tires. You cannot change anything on it, right? So and we're trying to get the industry to adapt to this. And I think we're the most flexible company also when it comes to business models. We offer 3 simple things. We do IP licensing. So we realize that there's Wi-Fi chipset vendors there that could integrate this without the need of gas and drive prices down, eliminate this DPD hardware entirely, and have a more reliable system across all conditions without really needing to test all conditions during the product development cycle. Again, it's that anti-spin system. You don't need to put it on all the roads in the world. You know that it works regardless of which road it's on.
Sure.
We do similar things that like our competitors, we're fabless and we do sell the silicon. And that's more directed towards OEMs and ODMs. The economics are great because this is a 300 millimeter wafer. We get lots of dies from each wafer, and the wafers are less costly in general. And that approach is through validated reference designs with the big reference platforms that exist today. And probably the fastest path to revenue for us. We also offer manufacturing license, which is a captive production for strategic partners who basically wish to have their own supply chain. And maybe they have efficiency advantage in that chain. So we offer that as well. So all you can eat buffet here.
I'm pushing this along because we're getting close to the end of the program here, but go ahead, Dr. Ali, and give us your final words, perhaps.
Well, the final word is that, like everything in the last 2-3 years, the challenge is to rethink architectures. And we've done that, and we did this and put it in silicon-based, something that was gas. And I think we're at the holy grail of what most RF companies like to do, and we managed to get there. And the future is, for us, we'll also scale a bit. We go to 65 nanometer in the same 300 millimeter process. We'll probably do a gas design probably in the next 12 to 16 months. At that point, we're not challenging gas. We're probably challenging GaN, because we think that there's same problems in that supply chain.
Dr. Ali, it's absolutely great to have you on the show. I think you do tremendous, very difficult, by the way, innovative work. There's not many of your kind, if any at all, except for you. So we commend you for your great work, and I want to thank you for coming on the show. And hopefully we've woken up a few more people to what you're doing, because I really think it is super important. So thanks for coming on.
Thank you for having me. Appreciate it.
All right.